They said something about like they're not allowed to have
Okay, so you get an idea of what he was working on. Pretty famous. While he was doing this, he began a correspondence with this woman here, Lady Ada Lovelace. She was the illegitimate daughter of Lord Byron. She considered herself a mathematician, and in fact, if you go through her writings, she actually had created a number of mathematical theorems. Of course, she didn't publish because she was a woman, but essentially they found things in her writings that predated the males who actually did publish them and get the credit for it. She was fascinated by Babbage's machines. She had a correspondence with him on it. And at one point, when he was saying, I have a mechanical system that I can use these cards to put the numbers in and then do calculations with them, she said, wouldn't it be interesting if you actually had some cards that told you the instructions to perform on the numbers? So her comment that essentially the cards could not only hold the data to work on, but the instructions to work on that data is considered one of the first suggestions of how a general purpose computer would work. So that's kind of the good about Lady Ada Lovelace. There's also a group of researchers who've looked and decided that actually she was kind of this society person. She was sort of that day's Paris Hilton. And she was kind of dabbled in stuff, and Babbage desperately needed money to make all these machines. He got enough money from the Royal Society to build one of them, and it didn't work. They claimed the amount of money he got from the Royal Society would have built a battleship. So he got a lot of money, it didn't work, he needed more money, and some people thought he sort of led her along, gave her mathematical theorems to write about so that she would talk in society and drum up interest in his stuff. The jury's still out on this, and in fact, Isaacson's book is actually very complimentary, and he did a lot of research on her life, so maybe I'm leaning towards she really did know what she was talking about, and she is the true first person to think of programming a computer system. Okay, on to the late 1800s, Alexander Graham Bell. We've got telephones, the latest technology, and in order to make telephones work, you needed rooms full of switches in the center of town that could connect everything. The latest technology involved electricity, and to make that work, we have these electromechanical relays. The idea is this is a spring-loaded piece of metal that when it moves down and makes a connection here, completes a circuit. And that would be thought of in today's computers as storing the number 1. When it's not connected, it would be storing the number 0. And you make this happen by running a circuit through this wire here, creating a magnetic current that actually pulls that down. So this was how switching systems were then created. When Turing went to, at Bletchley Park, do his decoding systems, one of the amazing things, and we'll talk about this, he developed this thing called the bomb that used electromagnetic relays that were developed for telephone switches, and this is thought of as one of the first calculating machines of our era. And I'll describe a little about what that did. Okay, then during the war, a group of people began to work with vacuum tubes. So the idea of a vacuum tube is you put electrical power here, it generates electrons. They don't get sensed by the anode unless you have another circuit coming in here that powers the grid. If the grid's powered, then the electrons travel across, and again, that's thought of maybe as a 1, whereas if it's not traveling, it's thought of 0. So the fact that these kind of switches could happen electronically without any mechanical system dramatically sped things up. And you're going to learn about a gentleman named Thomas Flowers who, when they created an electromechanical decoding machine that didn't go fast enough, he developed the Colossus at Bletchley Park that went much faster because he said it these vacuum tubes. Okay, and in fact, here he is. And this is the kind of interesting thing. The Post Office Research Station north of London in the 30s was the height of high tech. Just like over in the United States, we had Bell Labs. When the phones were the latest thing, this is where all the scientists and researchers were going there. And this gentleman, Thomas Flowers, was told to build an electromechanical system and to try and speed it up. And he said, it won't, it can't go any faster. But I know that these vacuum tubes will allow me to build a system that will go faster. And people said, no, we all know that vacuum tubes burn out. They're not dependable. And he said, well, yeah, that's true if you shut them off and on. But if you leave them on all the time, they're fine. He actually built the first electronic computing system. Delivered it to Bletchley Park. They didn't believe it until he turned it on, and it basically did what their electromechanical one did, a fraction of the time. The story of Turing has a tragic end, and there's a bit of tragedy to Thomas Flowers. Because of the Official Secrecy Act in England, no one could talk about this for 30 years. Flowers went to computer companies in England who were building electromechanical computers, and they said, you're crazy, you should be using vacuum tubes. And they said, yeah, sure, how do you know? And he couldn't tell them that he had done it and had proven that it worked. So everyone thought he was kind of a stuck-up, arrogant guy, when in fact he actually could have been known as kind of the creator of the very first programmable computer. So amazing guy. Okay, on to mathematical concepts and algorithm analysis. And the timing here is a little weird, but I think it's important to do it this way. I want to tell you about 1937, 21-year-old MIT graduate student named Claude Shannon. He wrote, and it's called the most important master's thesis ever published. It was a symbolic analysis of relay switching circuits. He combined Boolean algebra with those electromechanical relays and pointed out that you could actually perform Boolean logic with those circuits, and in fact do additions, subtractions, etc. And so he wrote this paper, and it got circulated. He talked with Alan Turing when Turing went over there to Bell Labs, and essentially this was the paper that suggested you could create something that could do calculations electronically. So here's some other stuff. So I almost think he eclipses Turing. He comes close. He's called the father of information theory. So think of these three things here and ask yourself how much this affects your life. First of all, he published another paper called A Mathematical Theory of Communication, where he described how binary data could be used to record anything. No one had thought of, oh, instead of numbers, this could represent music, or a photograph, or a movie. So essentially, everything you do digitally is because of this paper that he wrote. Then, if you transmit anything from your phone anywhere, Shannon was the one to create a method that would allow digital communications to be passed with error correction from one place to the other. And if you've ever bought anything, Shannon was the one who worked on the cryptography and coding systems that all the financial systems actually use to send things. So pretty impressive collection of stuff. Okay, now going backwards. Beginning in the 1900s, all the mathematicians are working on proving theorems, etc. And two very famous pair, Alfred North Whitehead and Bertrand Russell, worked on publishing the Principia Mathematica. The theory was that they were going to collect all the axioms that mathematics had. They were all going to be here, and there weren't going to be any more, and so this was everything that mathematicians needed to know. And it was actually something that went on, and people were actually thinking about it, and it's a pretty impressive document. And then came Kurt Gödel. Gödel published his incompleteness theorem that proved that it was impossible for this to be true. And it threw all of mathematics into disarray because he actually proved that everything they'd been working on wasn't going to work. Okay, At the same time, Turing did the same thing. So he created, and this is probably the most famous paper that Turing published. It's called The Beginning of Programmable Computers. It was called On Computable Numbers with an application to the, and the German word means the halting problem. And in order to get his proof across, so the proof is important to mathematicians, but to us interested in computers and computer programs, it's more important that in order to get his proof across, he created as a thought experiment a machine that's now known as a Turing machine. And Gödel said that he looked at this paper and said that this proof of the incompleteness theorem is actually better than his own. It's in this paper that Turing begins to talk about an automaton, something that takes instructions and does calculations, and he called it a computer. First use of the term computer for what we think of it as now. It's generally credited with starting multi-purpose programmable computers, but to understand why, we need to understand what this automaton thought experiment is about. So where did the Turing machine concept come from? It came from this. This is what was a computer in the 1930s. Women. If you were a woman in the 1930s and you were good at math, you either became a teacher or you went to work at a firm as a computer. That was it. In fact, Claude Shannon met his wife at Bell Labs, where she worked as a computer. Here's something I took a photo of at the Science Museum. Leslie Comrie created the Scientific Computing Service in 1937. And if you were a scientist and you needed to know what the position of the moon would be in 82,000 or how to direct an anti-aircraft gun, you hired these women to do the calculations. You gave them instructions on what you wanted to calculate, and they would use this and do the calculation. They do part of the calculation, pass it on to the next person who would do the calculation. That's how calculations were done. Okay. Turing came along with that idea of automatons, could be people, could be machines that were given instructions and could do calculations. And he created this thought experiment. He said, imagine that you have a system that has a series of states. And every one of these states, you're reading an infinite paper tape. And based on what you read on the tape and what state you're on, you'll write something to the tape, move to the left or right, and go to a different state. What these are that's essentially the very first computer program. It's moving from this state to this state is an instruction. So he created this. And it works. And in fact, you can go online and look at the YouTube video. People have created Lego Turing machines where they will do various things. Like you can make them add binary numbers or do almost anything. Here was the important thing, though, for us in terms of computers and what they could do. His moment of genius was he said he actually created a sequence of states. He created a program of what is called the universal Turing machine. It's kind of a recursive thing for all you AI guys. The idea is these set of instructions can run a set of instructions to be any machine possible. It was that concept that a machine could be general use and could run a set of instructions to do anything that became what inspired everybody to build computers. There's all the thought process, there's the technology, and now World War II happens. And so I'm going to jump to the idea of Bletchley Park, where in England, they were fighting the war against Germany. Germany had taken over all of Europe. They surrounded England with submarines and tried to starve England into submission. And it's this box here, called the Enigma box, that Germany would send all their instructions out to the German submarines, the U-boats. Okay, and so this is what it looks like, and I'm actually going to get out of my presentation because I can't make PowerPoint go to this, and I'm going to show just a little video on how this thing works.